Hey guys, welcome to the second video of this video series. So we were in module number 4 where we were discussing about pile foundation. Okay, so this is the question from the last class where we were given a column and that column was carrying an axial load of 750 kilonewton. There was also two moments. One was 50 kilonewton meter about the shorter axis and 35 kilonewton meter about the longer axis. Beneath the column we had 15 number of piles in a group, each of diameter 400 millimeters. Okay, and we were asked to determine the load acting on each pile. So we did that problem in a tabular format where we determined the axial load carried by each pile. But there is also a second part to this problem. So this is the second part. So what does it say? It says that the piles in the pile group have an effective length of 12 meter. So when I say the term effective length, you must have read in columns that there are many n conditions. Okay, there may be a column where the ends are hinged. Okay, this is a hinged column. There may be a condition where the both ends of the column are fixed. Okay, so when the both ends of the column are hinged, then the effective length is L. When both ends of the column are fixed, then the effective length is L by 2. When one of the end is hinged and the other end is fixed, then the effective length is L by root 2. So this is something you have learned in your design of structures. So these lengths L, L by 2 and L by square root 2 are called actually effective lengths. So in this question you are directly given the effective length of the pile. Anyway, then we are asked to design the piles in the pile group. Okay, we need to do the design taking the grade of concrete as 20 Newton per mm square. That means FCK is 20 Newton per mm square and grade of steel is Fe415. Okay, so let us see how to proceed with the design part. So this is the table from the last video where we determine the axial load carried by each pile. Now if you observe very carefully, pile number 5 carries the maximum axial load, that is 55.70. If you compare with the other piles, this value is the highest. Okay, so we will be taking pile number 5 and we will be designing this pile. Okay, so if this pile is safe, then automatically the other piles will also be safe, because pile number 5 is now the pile which is carrying the highest amount of load. Okay, so our target is to make sure that pile number 5 is safe. Okay, so let us see. So now I have written that pile number 5 carries the maximum amount of load. Okay, and what is the maximum amount of load carried? It is 55.70 kilonewton. Okay, now to this load I will be applying a factor of safety which is 1.5. Now whenever I apply a factor of safety, that load is known as factored axial load and it is denoted by PU. Okay, so when I multiply 1.5 to the axial load, that is 55.70, I get a value of 83.55 kilonewton. So this is my factored axial load. Now here's an interesting concept. Suppose this is my pile and this is the axis of the pile. Now I say that this pile has got an axial load of 83.55 kilonewton. Okay, now when I say axial load, it means that it is acting through the axis of the pile. Okay, so this is how the load is acting. But in practical case, the load may not always act exactly through the axis of the pile. Okay, it may act at a distance from the axis of the pile. There may be a certain distance between the load and the axis of the pile. So when there is such a difference between the axis and the load, it gives rise to something called eccentricity. So this distance is actually called eccentricity, denoted by E. Now in this case, in this problem, we do not know what is the eccentricity. So we have to consider the minimum amount of eccentricity present in our pile. So clause number 25.4 of IS 456/2000 says that the minimum eccentricity in a column or in a pile is equal to L by 500, where L is length of the pile, plus D by 30, where D is the diameter of the pile or the lateral dimension. And this value, the resultant value of L by 500 plus D by 30, should not be less than 20 millimeter. That means the minimum value should be always 20 millimeter. Now in our case, the length of the pile is 12 meter. Okay, then I have multiplied the 12 meter with 10 to the power 3, so that it comes in millimeters. So 12 into 10 to the power 3 divided by 500 plus 400 is the diameter of the pile divided by 30. So minimum eccentricity comes out to be 30 millimeters, which is greater than 20 millimeters. Okay, so when there is an eccentricity, it will give rise to bending moment. Okay, there will be a bending moment about the axis of the pile. If you look at this diagram, if the load is acting over here, and if this is the axis, then there will be a bending moment generated about the axis of the pile. Okay, so now let us calculate what is the bending moment generated about the axis of the pile. So how will I do that? I will multiply the axial load, okay, that is 55.70 into the eccentricity. Eccentricity was 30 millimeters, so in meters it will be 0.03. Okay, so this is the bending moment. Now if I apply a factor of safety, that is 1.50, then it becomes factored bending moment, which I denote by MU. So 1.5 into 55.70 into 0.03 will give you a value of 2.50 kilonewton meter. So this is the factored bending moment. Alright, the next step is to determine whether your pile is a long pile or a short pile. Okay, now this is similar to what we have learnt in columns also. How do we determine whether a column is a long column or a short column? We take the ratio of effective length of the column to the lateral dimension of the column. In this case, we will be taking the effective length of the pile divided by the lateral dimension of the pile. Okay, so what is the effective length of the pile? It is 12 meters. And what is the lateral dimension of the pile? It is 400 millimeters. So in meters it will be 0.4 meter. Okay, so this value comes out to be 30. So you know that if this ratio, that is effective length by lateral dimension, is greater than 12, then we say that the pile is a long pile or the column is a long column. So in our case, the value 30 is greater than 12, so the pile in our case is a long pile. Okay, now when the column or when the pile is a long pile, then clause number B 3.3 of Annexure B in IS 456-2000 says that if your pile is a long pile, then you need to apply a correction factor to your axial load and to your bending moment. So what is the correction factor? The correction factor is clearly stated in that clause, that is in clause B 3.3, and this value is the value of the correction factor. So correction factor is denoted by CR. So CR is equal to 1.25 minus L effective, that means effective length, divided by 48B. So what is B? B is again the lateral dimension. That means in our case it will be the diameter of the pile. Okay, so now I will be putting the values. So CR will be equal to 1.25 minus effective length is 12 meters divided by 48 into the lateral dimension or the diameter of the pile, that is 0.4 meter. So ultimately I will be getting the value of correction factor as 0.625. Okay, so once I know the correction factor, now I will be correcting the axial load as well as the bending moment. So what is the corrected axial load? Axial load that I have got previously divided by the correction factor. So previously I got the factored axial load as 83.55. That divided by the correction factor, that is 0.625, will give you a value of 133.68 kilonewton. Okay, so now this is the value of axial load that I will be using for designing my pile. Similarly, I do this process for bending moment also. My bending moment, that is the factored bending moment, was 2.50. Correction factor was 0.625. If you divide both of them, you will be getting a value of 4 kilonewton meter. So this is the value of bending moment that I will be using to design my pile. Okay. So this is a chart from SP16. This is chart number 57. So if you observe at the upper right corner, I have got a figure, right? So this is actually a pile, cross section of a pile along with the reinforcements. Okay, and here I have got something called D dash. Okay, this is D dash. This term is D dash. So what is D dash? If you see, it is from the edge of the pile to the center of the reinforcement, clearly indicated in the figure. So from the edge of the pile to the center of the reinforcement is what is known as D dash. So in other words, it is actually the effective cover. Okay, D dash is the effective cover. And then I have got the capital D. So capital D, it is marked as from the top to the bottom. Okay, so that means it is the diameter of the pile. And here you see there is a ratio, that is D dash by D. Okay, so D dash by D can be of many values. It can be 0.15, it can be 0.10, it can be 0.20. So accordingly I have got different charts. If D dash by D is 0.10, I will be having a different chart, that will be chart number 56. Similarly, if I have got D dash by D equal to 0.20, it will be chart number 58. Okay, so the charts depend on the value of D dash by D. Now you observe on the y-axis. Okay, y-axis is Pu by FCK D square. I don't know whether it's visible to you, but it says it is Pu by FCK D square, where Pu is the factored axial load. Okay, or in our case it will be corrected axial load. FCK is grade of concrete and D is the diameter of the pile. And if you see on the x-axis, I have got Mu by FCK D cube. Okay, Mu is actually the factored bending moment, or in our case it will be corrected bending moment divided by FCK D cube. Okay, so why we need to use this chart? We need to use this chart in order to know the percentage of steel required in our pile. Okay, because if you know the value of Pu by FCK D square and Mu by FCK D cube, you can get these values. P by FCK. Okay, P by FCK gives you the P means percentage of steel, FCK is grade of concrete. So by using this term, we can actually determine what is the percentage of steel required in our pile. So what is my target right now? My target right now is to know what is the value of D dash by D, so that I know which chart to follow. Once I know what is the value of D dash by D, then I need to know what is Pu by FCK D square, and once I know Pu by FCK D square, I need to know Mu by FCK D cube. Once I know both the values of y-axis and x-axis, I can find the value of P by FCK, and that will give me the percentage of steel. So that is the plan right now. Okay, so I begin with my plan. So I first find what is D dash. D dash is nothing but effective cover. So effective cover is what? Clear cover plus half of the reinforcement dia. RFT means reinforcement. Okay, so I have assumed that clear cover in my case is 50 millimeters. Okay, in piles generally we consider the side clear cover to be 50 millimeters, and I have assumed that the reinforcement which I will be using is 12 mm dia. So 12 divided by 2, this gives you the value of D dash as 56 millimeters. Okay, and capital D, that is the diameter of the pile, is already known to you. It is 400 millimeters. So the ratio of D dash by capital D is 56 by 400, that is 0.14. So it is quite close to 0.15. That means I can use chart number 57 for my design. Okay, so once I have fixed the value of D dash by D, let us find what is the value of Pu by FCK D square. So Pu, that is the corrected axial load, is 133.68. this multiplied to 10 to the power 3 so that it comes out in Newton. Okay, then FCK is 20 and diameter is 400, so 400 square, so I get a value of 0.041. Then I find what is mu by FCK d cube. So mu was 4. If I multiply this with 10 to the power 6, I'll be getting it terms of Newton millimeter. FCK is 20 and again d is 400. So this value gives me 0.003. Okay. So now let's look at the chart. If you look at the chart, pu by FCK d square is something which we can find along the y-axis. But mu by FCK d cube was 0.003, and you can see that the starting value itself is 0.05. So that means this chart cannot be used to determine the percentage of steel, since the value of mu by FCK d cube is very small. Okay, this chart is unusable for our purpose. So what we will be doing is we will be providing the minimum percentage of steel required in the pile. Okay, so minimum percentage of steel required in a pile is 0.4% of the total area, 0.4% of the total gross area. So if I need to know the area of steel, that is AST will be 0.4% of the total area. Total area is pi by 4 multiplied by 400 square. So this will give you 502.65 millimeter square. So that means this is the area of steel required in my pile. So if I know the area of steel required in my pile, I can easily determine how many numbers of reinforcement are required, right? So 502.65 divided by the area of one reinforcement bar gives you the number of reinforcement bars. So the number of reinforcement bars required is 4.44, so that is approximately equal to 5. And to be on the safer side, I provide 6 numbers of 12 mm dia bars in my pile. Okay, so finally I have decided that I will be providing 6 numbers of 12 mm dia bars in my pile. So this is actually the longitudinal reinforcement. Okay, now the longitudinal reinforcement needs to be tied, right? So I need to provide lateral ties. So these are the tie bars. So I decided that I will be providing 10 mm dia bars, okay, 10 mm mild steel bars, but I need to fix the pitch of the lateral ties. Now what is pitch? So suppose these are my longitudinal bars, okay, these are the longitudinal bars of 12 mm, and then I have got the lateral ties. So these are the tie bars which will hold the longitudinal bars together. Now the vertical distance between two lateral tie bars is actually known as pitch. So this distance is actually the pitch. Okay, so as per clause number 26.5.3.2 C of IS 456/2000, pitch of lateral ties should be always less than the lateral dimension. In our case, lateral dimension is 400 millimeters. It should be always less than 16 times the diameter of longitudinal reinforcement. So our longitudinal reinforcement is of 12 mm dia, right? So 16 multiplied by 12 will give you 192 millimeters, and it should be always less than 300 millimeters. So that means the pitch should be maintaining all the three conditions. It should be less than 400 millimeters, it should be also less than 192 millimeters, and finally it should also be less than 300 millimeters. So considering all the three cases, I have decided to provide a pitch of 150 mm center to center. So I finally write that provide 10 mm dia lateral ties at the rate of 150 mm center to center. So this is the design of your pile. Okay, this completes your design, but after that you need to draw the cross section as well as the longitudinal section. Okay, so if you look at the longitudinal section, this clearly states that the diameter of the pile is 400 millimeters. Okay, so this is the pile and these are my longitudinal reinforcement, these are my lateral ties. Okay, and the pitch is clearly stated, it is 150 mm center to center. Now this length is only a part of the entire pile length. Okay, so this length is not 12 meter, it is only a part of it, so I have shown it with this symbol. Okay, now if I take a section over here, if I take a section at AA, this is what I will be looking at, right? This is the body of the pile, the black color one. The green one is actually the lateral ties, which I have marked as 10 mm dia at 150 mm center to center, and the red dots which you see are actually your longitudinal reinforcement. So I have provided 6 numbers of 12 mm dia bars. Okay, so this completes your numerical. So if you have understand both the videos till now, then congratulations, because you will be getting this question for 15 marks in your exam. Okay, so this is one of the easiest problem in our syllabus. Hope you have understood everything. So if you have got any doubts, please write in the comment sections. So that's all for today. Thank you, and meet you in the next video.